All right, I'll try another one. Let's see. This is from chapter 37, and it's number 49. This is a lot like 48, so you might want to look at 48. Although 48, I used the reflection and the Young's double slit. This one, maybe I won't. I'll just say, here's what the problem is describing, that you have this transmitting tower, and it's going to send it to this house, kind of old school, where the house has an antenna. And so the radio waves, which they say are 350 meters long, go towards the house. But there's an interesting added effect, that there's this ionosphere where the radio waves, often referred to as the sky wave, so here's our ground waves and here's our sky wave. The sky wave goes up and bounces off the ionosphere, and so it's going to travel a longer path. And of course, how much longer depends upon this, I'll call it the vertical height of the ionosphere. And these two waves, when they come together at the house, they may be constructive or destructive. And if they're destructive, the people in this house are going to say, hey, I can't get the channel very clear today. I can't watch the TV. And it depends on the wavelength. So it's like, okay, I can't get channel 5 today, but I can get 7 just fine. And then, of course, the next day, the ionosphere could shift depending on weather conditions. And so it's like, hey, I can get channel 5 today. Which is, I guess, one of many reasons that the whole world has kind of changed to cable TV. We don't have to worry about any of the interference of the atmosphere and all the fun little details that has. But the cost is more, so we pay for cable. In old days, you just put up an antenna and it was free. And anyways, that's kind of this idea. But what we learned is that if there was a path difference, delta R, of a half wavelength, or 1.5 wavelengths, or 2.5 wavelengths, you would get destructive interference. And so this one is saying then that what is the, I better read it here, the lowest, or how does it say? It says, find the minimum height of the ionosphere layer. So they want this to be as small as possible, which will make the path difference this lambda over 2. And they say from here to the house is 30 kilometers. I'm just going to break that into 2. 15 kilometers each, because this from here to here would be 15,000 kilometers, then y squared, and then the square root. So that would be this path. And if I double that, that would be the whole path to the house. And if I subtract that, the straight line shot would be 30,000 meters, or 30 kilometers. And so what we're saying here is the path along here is bigger than the path along there. And if that path is exactly a half wavelength, these two are going to come together with destructive interference, and so you're not going to get a very strong signal. In theory, zero signal at your antenna, and you're going to have a hard time picking up that particular wavelength, which corresponds to that particular channel at that particular moment, or that particular conditions here. So now, of course, the wavelength that they told us is this 350. So when you divide it by 2, we're looking at 175. 2 times this 15,000 squared plus y squared minus 30,000. And so now it's just a matter of solving for y. So if I bring this over, this is 30,175. If I then divide it by 2, I then have the square root of 15,000 squared plus y squared. If I grab my calculator, that's 30 175 divided by 2. And so this is 15,087.5. Let me square it so that this becomes 15,000 squared plus y squared. So I will square that. And so this becomes 2276. Oh, maybe I'll just write that as times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8. And then 15,000 squared plus y squared. So y squared. Then let me take that number and subtract 15, 1, 2, 3 squared. And that would be y squared. So let me just take the square roots of that. And so we're looking at y as 1,600, and I'll just call it 23 meters above the ground, or 1.623 kilometers above the ground. Yay.